Hi, my name is Michael de Podesta, and this is a talk about replacing a gas boiler with a heat pump. I'm going to give this talk tonight to the Richmond, Twickenham Friends of the Earth over at Twickenham at the Exchange. Okay, let's get on. So this is a very long talk with lots and lots of detailed bits in it. So I thought I'd start with the end. What's the summary? This is the summary, and this is why this matters. For most people, replacing a gas boiler in their home with a heat pump is the most significant thing they can do to reduce carbon dioxide emissions from their life. It saves, we'll come to the calculation later, but it saves tons of CO2 easily each year. And the reason I'm giving this talk is that in a rational world, we'd be falling head over heels to install heat pumps in our homes. But the move to using heat pumps means an end to a very profitable business for fossil fuel companies. And they are doing everything they can to slow down the rate of change. And the way this is done is standard operating procedure is to use FUD. Fear, uncertainty, and doubt. And so, having learned about heat pumps as a physicist, and having had one in my home for a year, this talk is about getting rid of that fear, uncertainty, and doubt, and allowing you to make rational choices for yourself. Okay. Enough of that. So this was the plan that I agreed with the Friends of the Earth organisers. It's got 25 items in it, so we'd better get on as quickly as we possibly can. So how heat pumps work. Now, I have a whole other videos on how heat pumps work, but it is worth to just summarise how they work, because they work in a different way from electrical heaters. So an electrical heater, this is a convector heater, you put in electricity and out comes heat. And all electrical heaters are 100% efficient, whether they're a radiant bar fire, a convector heater, or a fan heater, or an infrared heater. They're all 100% efficient. It's part of the physics, and 100% is not bad. Gas is not quite so good. You put in chemical energy, so you find gas, transport it through all the pipes and use lots of energy to do that, and you bring it to your home where you burn it and you release the heat, but you only get about 90% of the heat you could get. About 10% goes out the flue, and if you've got an old boiler, it could be 75%. We'll revisit this question as we go on. Heat pumps are different. They don't make heat, they move heat. And you already have one in your home if you own a refrigerator or a freezer. Now, a refrigerator or a freezer is basically an insulated box. It's got quite thick walls, that's insulation. And in the back of it, or in the middle of some of them, or at the bottom, there is a heat pump. And what the heat pump does, you activate it with electricity, it does its heat pump magic, and it moves heat from the inside of the box to the outside. And you can see that, so in a freezer, for example, it will move heat from minus 20 Celsius. It'll keep cooling down to minus 20 Celsius. And then it heats up the room that the refrigerator is in. So the outsides of the heat pump typically warm up to about 30 degrees Celsius, and that warms up your home. So that's around the back of the refrigerator, or around the sides of modern refrigerators. And so the trick for using a heat pump to power your home is that you concentrate on this bit instead of this bit. We think of heat pumps as getting things cold, but actually if you just keep this, just concentrate on this bit. So if we just put some insulation around this bit, and then we take away the insulation around that bit, then what we're doing is we're moving heat from a cold place to a hot place. And this could be your home. And so you just operate the heat pump and you move heat from outside to inside. Great trick. So typically you don't want 30 degrees in your house, you want 20 degrees. And typically it's only at most 0 degrees Celsius outside. And that's what heat pumps do. They move heat from outside where it's cold. So we'll come to that in a moment. So where do you get the heat from outside? Well, you can get it from the air outside, or you can get it from the ground outside. And there are devices that do both of those things. And then how do you get the heat into the house? Well, you can transfer the heat from this thing directly to the air and blow it around the house, or you can transfer it to water and flow the water around radiators in your house. And so there are typically 3 types available of heat pump. There's air-to-air heat pumps, air-to-water heat pumps, and ground-to-water heat pumps. And we'll see what they do. But for all of them, the key thing, just summarizing, is they move heat. So you put in maybe 1 unit of electricity, and this is the magic. The magic is that you can move 2 kilowatts of heat. So you add these things together and you get 3 kilowatts of heat, even though you've only put in 1 kilowatt of energy. So that's absolutely fantastic. They're 300% efficient, which sounds like it can't be true, but it is true. Now, their efficiency is called the coefficient of performance, or COP, and we'll be using that term right throughout this talk, COP. And the heat pumps work best when they're only pumping through a small temperature difference. So if it's very cold outside and you want your house very hot, then that's very hard for a heat pump. But if it's not so cold outside and you don't want your house quite so hot, that's really good for a heat pump. So for the heat pump I've got, this is the seasonally averaged COP, and this is versus the temperature of the water in the radiators. So if the temperature of the water in the radiators is only 35 degrees, I can get 450% efficiency, a COP of 4.5. But if I want the water temperature to be 55 degrees Celsius, then I only get 300% efficiency. Only 300% efficient. No, that's terrible. But it's this efficiency I want to focus on. This 300% efficient is what makes the electrification of heating possible. It's absolutely essential. If you take 1 unit of renewable energy generated by wind turbines or solar or low carbon electricity from nuclear power stations, and if you decide to if you use that to heat homes, you get 3 units of heat into homes. If you decide, because you're a shill for the fossil fuel industry, that you want to turn it into hydrogen and ship hydrogen to homes, you get a half a unit of heating in your home. So heat pumps are 6 times better than using hydrogen before you even go into the other disadvantages of hydrogen. So 6 times better. That means that to get a renewable energy infrastructure in the UK, we need 6 times less 6 times fewer wind turbines, 6 times fewer nuclear power stations, 6 times fewer solar energy plants. It's just transformational. Heat pumps are engineering magic. Okay, I'll stop going on about that. So let's take a look at air source heat pumps. That's the most common type of heat pump, and just look in detail at how it works. So this is what the unit that sits outside the house looks like. This is where it captures the heat from the air. There's a big fan just behind this grill here, and it takes heat out of the air. So it's operated by electricity. You put cold water in from your house and you get hot water out. That's it. And that's used to warm the house through radiators, and it's used to produce hot water for the showers and so on. Now, how does a heat pump work? I won't go on and on about this, but it's basically a pipe, just a long tube, literally, and it's filled with a working fluid. A working fluid is a fluid like butane, that's like lighter fuel or something. There's a whole range of them available, and they typically exist as a combination of liquid and gas together. And as they go round here, there's a pump that pumps the working fluid round and round here, and the amount of liquid and gas changes. And there's an expansion valve, and what happens is that you pump it round here, it gets expanded, and on this side, when the fluid expands, it becomes cold, and then as it comes around here it's compressed, and when it's compressed it becomes hot. So just to show that, I'm just going to change the colors of the pipes here. So now this hot on this side, cold on this side, and the way it works is you make this tube here extremely long. It's many meters long in practice and really quite small, and then you blow air over it. So this is from outside, so you're blowing or sucking air over these tubes, and because the working fluid is cold here, the heat from the air, so the air might be at, let's say, 0 degrees Celsius, but your working fluid, it might be at -10 degrees. And so heat from the air flows into the working fluid and is captured in the working fluid, and it comes through here, then it's compressed. And when it's compressed, you run a pipe from your house with cold water next to where the working fluid gets hot, and the heat is transferred from the working fluid to the water. So out comes hot water. That's how they work. So here the working fluid is hotter than the water, and so the heat flows from the working fluid to the water. So overall, we've taken heat from the air and put it into the water. So an air source heat pump is normally an air to water heat pump. That's the trick. So this is in the heat pump I showed you. If you look inside it, there's the fan, and when the fan operates, it's sucking air through this very long pipe. So if you look at this pipe here, it looks like this. It's got loads and loads of fins, and you can just see the pipes here, and the working fluid flows through those, and as the air flows over it, the heat flows from the air into the working fluid. So there's the heat pump operating. The working fluid's just going round and round. It gets cold over here, the heat flows in, it gets hot over here, it goes into the water, and then you've got your central heating pump that just pushes the water around through radiators and keeps your house warm. That's how it works. Now a ground source heat pump, it works in a very similar way, except instead of capturing heat from the air, it captures it from the ground. So you bury that very, very long pipe in the ground to catch the energy. So the heat flows from the ground to the working fluid, and here the heat flows from the working fluid to the water. So that's a ground to water heat transfer overall. The working fluid never escapes, it just goes round and round all the time, moving heat. You can think of it like a sort of conveyor belt with a bucket. It's sort of capturing heat here and bringing it to a higher temperature and tipping it up here and going round and round. This is a rather petite picture of a ground source heat pump. As we'll see in the next slide, it makes it look like you could put it in a reasonable house. You can't put ground source heat pumps in reasonable houses unless you've got a lot of money. So ground source heat pumps can be more efficient than air source heat pumps for one simple reason, that 1 to 2 meters below the earth where the pipes run, it doesn't get very cold. So on the coldest days in winter, it gets maybe around here, it gets maybe -3 degrees Celsius, whereas a meter below ground, it's probably only 10 degrees. So that makes the temperature difference for moving the heat much smaller, and it makes it very easy to, that makes the pump easier to operate. The problem is that you need to do this to your garden or paddock, which would be more likely. And the rule of thumb is that if you want to heat a house of a given floor area, you need 2.5 or 3 times the floor area outside. So my house is 167 square meters over 3 floors. So that requires 500 square meters of land, i.e. 50 meters by 100 meters. That's the size of the block that this house sits on which there are probably 50 houses. So if you've got, so it's just not a practical choice. Now you can do these things vertically. You have to drill 100 meters down, a hole 20 centimeters diameter. And one borehole like that gives you the possibility of about 6 kilowatts of heat extraction. Basically, ground source heat pumps are not practical. I will say more about them as we go. Now, air-to-air heat pumps are practical, and people often don't think about them when they're trying to switch their heating. So here's this little diagram again showing an air source heat pump. So there's the working fluid going round and round, and here the heat goes from the air to the working fluid. Here it goes from the working fluid to water, and then the water then flows through the circuits, the radiators in your house. Now, an air-to-air heat pump is also called an air conditioner, and it works, this bit is very similar. You've got the working fluid going around it, but the working fluid leaves the outside unit, and the working fluid goes inside into a unit like this. This is called a fan coil unit. And it transfers the heat to the air using an arrangement of pipes and fins, rather like the photograph I showed you of the inside of the heat pump. And then air is blown over that. And the advantage of this is that to heat your house here, you might have to go to 55 degrees Celsius water. So that's quite a big step up here. But here, you might have to only go to 30 degrees Celsius to heat the air in your room. So these can be very efficient for heating. So air conditioning that's an air-to-air heat pump. So the thing you're probably looking for if you're thinking of doing this is a mini split system. It has one outdoor unit that's just like the air source heat pump, and it's connected to up to 5 indoor units. And they're very good for small apartments or open plan homes. It doesn't produce hot water. You've got to get a solution for that separately. But it does have some good things. The bonus is that it provides cooling in summer heat waves, and that can be very, very valuable. And if you're looking online, these appear to be incredibly cheap. So the price tip is to double the prices you see online to get an installed price. Okay, so just comparing those again. So we've got air to air, air to water, and ground to water. And I'm going to mainly talk about air to water heat pumps for one reason, which is that they represent a direct replacement of a gas boiler. They will heat your hot water and provide space heating to your house. So we're going to talk about air to water heat pumps, but I thought I'd mention the other types. So assuming you're moving from a gas boiler, what's the difference between using a heat pump and a gas boiler? Well, the key difference, there are two key differences in the way it makes hot water, but also in the way it heats your house. That gas boilers, even small ones, are very, very powerful. They use a lot of gas. So typically they might have a heating power of almost 20 kilowatts. It's very common to find a 30 kilowatt gas boiler in homes. And so typically they will they'll heat your home for 10 minutes, push hot water around your radiators. You'll feel the radiator very, very hot. And then they'll switch off for 40 minutes. And now the average amount of heat that you require in your home might only be 5 kilowatts. But your gas boiler supplies it in 20 kilowatt bursts. So that's very inefficient from the boiler's point of view, and it's not how heat pumps work. Heat pumps try to match this average requirement. So the problem in using radiators to do this is that for a gas boiler, you can put in water at 70 degrees Celsius and it'll go through your radiator and come out at 65. And that might transfer 1,000 watts of heat into your room through convection and radiation. Mainly convection, by the way, in most radiators. But for a heat pump, maybe you're only going to reach 50 degrees Celsius with your hot water, and that difference from 70 Celsius to 50 Celsius roughly halves the heat output. So the radiator's only going to put out half that amount. Now that's no problem if the radiator just operates for longer, because in this one we saw them in most homes, the heat switches on and then switches off again. So you need to understand that the radiators will operate for longer but at a lower temperature. So So here's a bonus energy saving tip. So you're probably not going to put a heat pump in this winter if you're still operating with a gas boiler. The efficiency of a gas boiler depends on the temperature at which water returns from the radiator. So if you're putting in 70 Celsius and it's coming out at 65 Celsius, then if we look on here, 65 Celsius, you can see you're only going to get about 87% efficiency. Why? Because the way you get this extra efficiency in boilers is that as you burn the gas and you get this hot exhaust, and you take as much energy out of that as you can, but if it doesn't cool down, there'll be a lot of water vapor in there. And if you can cool the water vapor, if you can get it below 58 degrees Celsius, it will condense and release extra energy. You see, you get this efficiency boost. They're called condensing boilers. So what you should do this winter, if you're still using a gas boiler, is try turning down the flow temperature. So what will happen is, instead of trying to heat your house like this, if you turn it down, you can get the same heating output, but at a lower flow temperature. The pump will just operate for longer. And if you can go down to here, it'll operate continuously. And so if you can get your temperatures down to this sort of level, you'll have no problem using a heat pump. Now, that for this winter, these three curves all give out the same heat into your house. But here the boiler efficiency is 94%, and here it's 85%. So you can save 11% on your gas bill with no change in the comfort level in your house if you just turn down the flow temperature. So let's talk a bit more about COP and SCOP. So COP is the heat energy output divided by the electrical energy used. And here's a sort of standard diagram. Typically 1 kilowatt hour of electrical energy moves 2 kilowatt hours of heat and produces 3 kilowatt hours of heat within your home. That's called the coefficient of performance, the ratio of this one to this one. And SCOP is the seasonal coefficient of performance. So that's affected by that's the average of the COP over a whole heating season. And it's affected by the source temperature. So if it's very cold in the winter, the SCOP will go down. And if you try to heat your house very hot, the SCOP will go down. So this shows how the coefficient of performance varies from my house over 1 week in January 2022, from the 1st of January. And the red line shows the outside temperature. The green line shows the flow temperature in the radiator, and the orange line shows the temperature of the house. So you can see the temperature of the house basically didn't change. It's 21 degrees more or less. But the outside temperature went from being about 13 on January the 1st to -3 on January the 6th. And you can see that here the flow temperature was automatically adjusted to be about 30 on that day. But then as it got colder, the flow temperature went up, and we put out that it was about 42 degrees or something on this very cold night. So let's look at see how the COP varies. So how does the energy vary during that week? So that's this mild day and this cold day. So the energy, the purple dots here show the thermal output, and this shows the electrical input. So you can see on this very cold day, the electrical input was, I guess I can't read this very clearly, it's about 1 kilowatt or something like that. And this is about 3 kilowatts output to heat the house on that cold day. Here the thing kept switching on and off, it's very hard to see. But we can evaluate the COP. So here's the COP. So you can see on this mild day, excuse me, on this mild day, the COP was between 4 and 5. It was operating between 450, about 450% efficient on that day. As we came into this very cold night, you can see on that cold night, it went below, the efficiency went below 300%, below the COP fell below 3 to about 2.5 mostly. This very low one is where it was doing the hot water as well. Anyway, it's going, that's COP, so it's varying from 4.5 when it's very mild to below 3 when it's very cold. Now, over the winter, this is the amount of heat that's delivered per day. So it's rather low in August and September, and then you can see it peaked up. We're delivering about, on average, about just less than 50 kilowatt hours of heat each day. Of course, so that's using much less electricity than that. At the peak here, we'd be using about 15 kilowatt hours of electricity per day. And this is how the COP varied month by month. And if you average it based on how much heat is moved, you get this SCOP, which for my system came out at about 3.6 last year. So that's how the system heats the house. How does it heat domestic hot water? Well, here's the basic heat pump operation, and here's the in normal operation, the water is flowing around here, and it comes round and it keeps being heated, and you're heating your house. But when you want to heat the hot water, you move this three-way valve, and now the heat pump has a separate mode, and it goes round and it heats the it passes water through here, and it transfers it to the water that you're going to drink or wash in. And typically it does that for an hour, and then it switches back to heating your home. Now the tank here looks something like that if you cut it away. So these are the pipes in which you can flow the water from the heat pump, and it transfers it to the water that you're going to use to wash in and so on. You can see they're typically very well insulated. Okay, so let's take a look at that. So this is that same week. Remember, this is the house temperature, the outside temperature, and the flow temperature. And now on this, I'm going to additionally show where we were heating water. So this shows the water heating up to just over 50 degrees Celsius. You can see here on this very cold day, that's where the water was heating. Even though it was -3 degrees Celsius, it was still warming the water up to above 50 degrees Celsius. So you can see that it's operating once a day, because that matches our requirements. But looks like on January the 3rd, we must have had some visitors. Maybe the children were back home, and we ran it twice a day, because if you need more hot water, you just run the cycle again, and it takes about an hour to top up the cylinder. And as it runs, you can, if you care, you can monitor the electrical usage. So you can see that as the cycle starts, the pump isn't working very hard, and it has to pump harder and harder as you go through there, because the temperature of the water has to be heated hotter and hotter as it goes through the cycle. And you can see the thermal output. At first there's a lot of thermal output, and at the end it's falling here. But anyway, you can see we're heating up to 55 degrees Celsius. So a big question, that's how we've done space heating and hot water. Big question is, do I need to insulate my house first? And the answer is no, you don't. I think this is a sort of a cultural leftover. There was a time a few years ago when putting in a heat pump was a very, very unusual thing to do, and people would only do it. They had a lot of fetishistic beliefs about it, that you must first do all these rituals of insulation in order to justify the wonder of a heat pump in your home. And certainly doing some insulation things is a very good idea. Loft or roof insulation, reducing drafts, updating glazing. These are all very smart things to do before you put a heat pump in. If you're really keen, you can put in external wall insulation. I did that, and it reduced the heating demand along with these measures. It reduced the heating demand in my case by about half, but just external wall insulation, the heat pump size renewed by 40%. And it'll reduce your bills by 40% as well. And you can do a bit of internal wall insulation. It's not as effective as external wall insulation, but it can be useful at the front of houses where people don't want to put external wall insulation on. But external wall insulation is good for the backs of houses or the sides of houses, even posh Edwardian and Victorian homes. But you don't need to do insulation first. So just get a bigger heat pump. So if you look at the minimal insulation here, take this big old house with minimal insulation, it might require a 12 kilowatt heat pump, and that might cost, the heat pump itself will cost £6,000. After extreme insulation, you might get away with a 7 kilowatt heat pump. This extreme insulation is probably going to cost you £20,000, but it's only going to save you £2,000 on your heat pump. Now the other side is that if you go with a bigger heat pump, you might possibly have to upgrade radiators. That might be more likely. So what power of heat pump do I need? Well, I've written a whole video on this, and the problem is that all gas boilers in houses are overpowered for heating the houses. They're designed to heat water from 10 degrees Celsius to 40 degrees Celsius in a few seconds, and that's where their size comes from, this instant water heating. But the actual heating of a house is the UK average heating required is about 6 kilowatts. Now the heating power that you require to heat your dwelling, it varies with the outside temperature. So this shows the heating demand along here. This is measured in my house. This is the temperature below the temperature of the house. So this was when we had the house set to 19 degrees Celsius. And so here it would be 14 degrees of demand. So it would be 19 minus 14, that'd be 5 degrees on average outside. And so as it gets colder, the demand for heat goes up. And so what you want to do is size your heat pump to cope with the coldest likely day that you're going to encounter. So before we talk about the size of the heat pump, there is some nomenclature that we have to adjust ourselves to. So this is the design temperature. That's the lowest temperature that's likely to occur in your area. In TW11, it's about -3 degrees Celsius. Heating demand, that's the difference between the inside temperature, which might be 20 Celsius, and the outside temperature. The maximum heating demand is the difference between the inside temperature you want and the design temperature, -3 in this locale. And the heat transfer coefficient is a measure of how well insulated your home is. It tells you how many watts of heating you require to warm up the house by 1 degree Celsius. So for an old house, it might be 400 watts per degree Celsius. So if you want to be, the heat pump power is then this 400 watts per degree Celsius times the maximum demand, 23 times 400, that would be 9,200 watts. And then to pick the heat pump, you'd pick the next size up that could match that. Now, how do you work out what size heat pump you require? And the answer is you don't. What happens is when you have the installation, the people come, they will be accredited by the Microgeneration Certification Scheme. Why will you get a MCS installer? Because that's the way you get a government grant of £5,000 to help you install your boiler, install your heat pump. So they will measure the size of every room in your house, the size and type of windows, which walls are internal, which walls are external. They'll measure the size and type of the radiators, and they'll do a big calculation. They'll work out the heating power required in each room to keep it at the desired temperature when the outside temperature is at the design temperature, -3. And then they'll work out whether the radiators can output that much heat when the flow temperature is, say, 45 degrees Celsius. And this determines whether the radiators are going to need upgrading. they'll add up the heating required in all the rooms to work out the size of the heat pump. Now there is a problem that this survey, particularly in the hands of inexperienced surveyors, tends to overestimate the required size of heat pump. So I've invented a rule of thumb to help you. So you can watch the rule of thumb on rule of thumb video on YouTube here. And the rule of thumb is very easy. So you take your annual gas usage in kilowatt hours and divide by 57.3, and that will tell you the heat transfer coefficient for your home. So this was for my house before any of the changes, and it was about 262 watts per degree Celsius. And it tells you the heat pump size is you just take your annual gas usage and divide by 2,900. So that says we would have needed a 5.2 kilowatt heat pump. So it's a rule of thumb. It's not a law of thermodynamics. It's not infallible, but it's if the rule of thumb estimation for your heat pump comes out very different from the MCS survey, you should have a word with your installer. Which make is best? Well, installers typically prefer to install just one or two manufacturers. They won't just pick any one. They might if they're very good, but they get very good at installing one particular brand. They know all its idiosyncrasies, so you may not get the choice. But from following heat pumps on Twitter, I don't know of any bad choices. I installed this one, Valent Aerotherm Plus. It's fine. The software is not great, but the physical quality is outstanding. The EcoDan from Mitsubishi Corporation, but they're made in the UK. They're the longest standing heat pump installers in the UK. And Daikin have been chosen by Octopus Energy. The Octopus Energy are trying to really boost heat pump installations, and they're installing Daikin ones. But there's also ones from Nibi, Sanyo, Samsung, and lots of other names. But I don't know that there are any bad choices. See what your installer offers you. Weather compensation. Now you've already seen weather compensation in action. So weather compensation is an alternative to controlling a heat pump with an on-off thermostat. So you may have something like this in your house or like this, and that's indoors. And when the temperature gets too hot, it tells the heat pump or the boiler to switch off. And then when it gets too cold, it switches back on again. That's the thermostat. But weather compensation doesn't work like that. It measures the temperature outside your house, and it adjusts the flow temperature in the radiators or underfloor heating to match the heating output to keep the inside temperature constant. So you have something like this on the outside of your house, and this is the net result of it. Here's the house temperature, here's the outside temperature, here's the flow temperature, and this is the same week in January. And you can see that as it gets cold, the flow temperature adjusts, but the temperature inside the house barely changes. These little wiggles here are when it switches the heating off to do the domestic hot water heating. So that's weather compensation. When it gets cold, flow temperature goes up, and this is a really efficient way to heat your house. So do I need new radiators? So here's that same slide I showed you before. The question is, when you get lower the flow temperatures, as you will when using a heat pump, will there still be enough heat to heat your house? So this is the same graph I showed before, and this is a test you can do now. If you lower the flow temperatures on your boiler, as well as saving money, you can also test whether your radiators are heat pump ready. So if you lower them like this, all these different things will have the same heat output in your house. So wait until there's some cold days and lower the flow temperature on your boiler until it's on all the time, continuously. And if that temperature is less than 50 degrees Celsius, then your radiators will be just fine for a heat pump. So just to say about radiators, that they transfer heat in two ways. One is by convection. The air flows past it and it rises a lot. Each surface of the panels transfers heat to the air and the outer surface here radiates heat. And so if you have hotter radiators, you can transfer more heat, but that will reduce the COP of your heat pump. If you have bigger radiators, and bigger radiators, not just more area, it's also more panels, or you can have little fins attached on here. If you have more fins, and if you make them a bit thicker this way so you can have extra panels, then that transfers more heat at a lower temperature, and that increases the COP of your heat pump. So here are different designs. So looking from the top, so here's a panel with water flowing through it. This one's got 2 panels with water flowing through it, and this has got 2 panels in it. Each one has got fins on it, and there's a whole sort of code about that. And you can see for a given area, you can go from 1.5 kilowatts to 2.7 kilowatts. So these radiator designs can be very, very effective at transferring heat. So this graph shows how the heat transfer from a radiator with 2 panels, a front one and a back one. So this is the amount of heat that gets transferred by radiation. This is the amount of heat that gets transferred by convection. And the black line is the total amount of heat that gets transferred by each mechanism. And you see when the water temperature is 70 degrees Celsius, it's up at about a kilowatt. But when you lower to 50 Celsius, it's just under 600 watts. So it's almost halved. So that's why you may have to look at your radiators. Now, so I made this whole big plan, and your MCS survey will come out with a plan like this for you. It'll show you all the rooms, the size of the radiators in that room, the area, and it'll work out what flow temperature you need to match the heating requirement of that room, and that'll tell you whether you need to replace the radiators. And the last thing I'd just say is these are all radiators, and so it may be a chance to funk up your home. I was really keen to get radiators like this, but my wife was not so keen. So we're past these sort of technical things now about heat pumps. Let's look at installation. So choosing an installer, it's very difficult. It's very difficult to know. Installers are really busy. I mean, they're all crazily busy, and it is, you're grateful if somebody comes and pays attention to you, especially if they're doing it up front on spec. If you're going to try and get 3 quotes for this thing, good luck is all I'll say. So I used a company called Inhabit, a very straightforward, very good company, probably not the cheapest, but very, very good. They're based in London. But HeatGeek is a website which has a searchable map, and you can look around London for installers. And maybe you want to ask Octopus Energy about getting a heat pump. They're trying to get big scale in installation, and so they're trying to automate systems and make it as rapid as possible. Remember, most installers will only work with 1 or 2 heat pump manufacturers. The physical size, well, they vary, and the bigger power, the more air you've got to extract the heat from, and so they get physically larger. So this might be a 3 or 5 kilowatt one, and this might be a 12 kilowatt one or something like that. So they're typically, the big ones are about 1.8 meters high, the normal ones about 1 meter high. I'll show you some pictures in a moment. And there are restrictions on where they can be placed. Your installer will advise you on that. So you do need pipe work, and the pipe work from these things is not the 15 millimeter pipe work that comes with that you normally see going into a radiator. It's the larger diameter. It's 22 millimeters is required at least to go from the heat pump here, because the heat pump needs a big flow of water through it to operate effectively. So these pipes here going to your hot water tank need to be at least 22 millimeters. Now, depending on your installation, especially if you're not replacing the radiators, then you may need a device called a low loss header, which is basically just a big pipe. Let me just zoom in on this bit here. And what happens is that the heat pump supplies a big flow of water, 20 litres a minute, at the temperature you want. And then the water goes round and round like that from the heat pump, and there's very low losses. It's very easy for the heat pump to do that pumping. But then to get it around your house, you have an auxiliary pump, an auxiliary central heating pump that pulls off just a few litres a minute to go around your radiators, and then it puts the cold water back here. And so this allows the heat pump to operate very efficiently, even if you've got rather poor pipe work in your home. So where can you put them? So they can be placed down the side or at the back of a house. They can be down the garden. They can be raised up on a wall. They can be at the top of a flat roof or extension, or even on the roof. One point I say is that in the winter, water comes out the bottom of them, and in the winter that water can turn to ice. So you may need to have a soak away underneath it, and you certainly need a good support to support the cylinder. A cylinder location typically requires at least 80 centimeters by 80 centimeters of floor area, and there are lots of other bits that go with that. I'll show you some pictures in a minute. So these are different locations. So here you can see the pipe work going into this. Looks like a Mitsubishi Ecodan one. This, I don't know what that one is. Looks rather smart there. This is tucked away around the side of a house. That looks like Samsung. This is LG. You can see here the insulated pipe work going. So that's going on the outside of the house. So rather than putting that pipe work through the inside of the house and destroying all the beautiful kitchen work, that's going up probably to where the hot water cylinder. You can put them on arms, supported wherever you can get them out of the way. You look here, you can see the plinth that it's on. These people appear to have, it looks like a Jacob's biscuit tin underneath here catching the water. That's not recommended. And these are all just other pictures of heat pumps. And this is a design, obviously, I don't know if you can actually get this, putting it in the loft. And this is the heat exchanger. So the one problem with heat pumps is that many people have switched to combination boilers, and they've got rid of their domestic hot water tank that they used to have. Well, that's just the thing that's happened. But for a heat pump, you've got to have some kind of hot water store. So if you cannot absolutely fit a cylinder in, then what you can do is use a thermal store. So these look like this. They're not cylinder shaped, they're box shaped, and they can fit under workspaces. They take up, for the same equivalent heat storage as a cylinder, they take up about a little bit less than half the space, and they can go under worktops and in cupboards and so on. And they're potentially useful, particularly in apartments or studios. And they work by inside. They've got a liquid which is like that gel you have in hand warmers. It's sodium. Can't remember the name of the chemical, and it's melted using and that stores heat in the in this material. And then when you want hot water, you just run water through it and it warms up. So this person, this is someone I know on Twitter, installed, this is his heat pump outside at the back of his house, and he installed his outside. So this is one of these hot water stores, and he built a little unit, an insulated box for containing it outside, which you may be driven to in extremis. So this is what we did. We remodeled our bathroom, and we have a corner unit here. It's about 80 by 8, fits in about 80 by 80, and it has these panels come off for access, and you can see that inside there's a lot of gubbins. There's all kinds of pipes. That's the low loss header. This is the control unit for the heat pump. All kinds of stuff. Okay, we're on to the closing stretch now, thank God. Noise. Heat pumps are not noisy. They're just not noisy. There's nothing I can say about it. I've had so many people come round, and as soon as they hear it, they just say, "Oh God." It's part of the fear, uncertainty, and doubt thing. It's do I leave it on all the time? Well, it's up to you, really. Personally, I leave our system on 24/7. It just keeps the house at 21 degrees all the time. It never changes. But some people like to set it back so that overnight the temperature goes down to maybe 15 or 16 degrees or so on. Now the problem is that if your house is well insulated, then it won't cool down very quickly. But you can still do it. But if your house is poorly insulated, it'll only warm up slowly. Anyway, I haven't really found the need to do that. Does it work when it's cold? Yes, obviously it works when it's cold. Heat pumps are widely deployed in Scandinavia, Poland and Germany, which have much colder winters than we do. And the heat pump in your home is happily keeping your freezer at -20 right now. So heat pumps have no problem working when it's cold. Does it get water hot? Yes, obviously it gets water hot. So some heat pumps limited to 50 degrees Celsius water. So that's very hot water. You won't be able to hold your hand in that. Others can heat water to 70 degrees Celsius. That is dangerously hot water. Legionella protection. So wherever you store water, you need to worry if the water spends a lot of time between 20 Celsius and about 40 degrees Celsius. They're Legionella bacteria that can be harmful. Not if they're swallowed, that's fine, but if you very fine mist, if they go into your lungs, they can give you Legionnaire's disease, which is pneumonia, basically. So the risk of infection is extraordinarily low. So I don't know of any cases. I have looked. I don't know of any cases of Legionella that have come about from domestic installations. They all come about from industrial air conditioning. So Legionella are killed in water at temperatures above 50 degrees Celsius. So heat pumps offer a Legionella cycle, which will heat water to 60 degrees Celsius, and I do this once a week. It's probably unnecessary, but I do it anyway. So this was over several days last year. I evaluated what the COP was for heating water to different temperatures, and heating water to 70 Celsius, the COP was down at about 2.5. But then when I was heating water to 60 degrees Celsius, the COP was about 2.9. It seems fine to me. Okay, getting on to the very, very closing parts of the talk now. I'm sorry it's taken so long, but we come to the important bit. How much does it all cost? So I got data from the boiler upgrade scheme that the government have been running. This is the start of it from May to July. And there's got air source heat pumps and ground source heat pumps. And the average installation cost was, so this is just under £13,000 for an air source heat pump. The government will pay £5,000 of that direct to the installer. So you would pay £8,000. Ground source heat pumps, you see, are like £28,000. So, you know, it's just a completely different type of endeavor. And the average size of heat pump was 10.7 kilowatts. That's probably a fair degree of oversizing in that, or these may be only people with big houses have applied. Your heat pump will probably be a bit smaller than that. So the average cost is about £8,000. And that's actually what I spent. So will you save money? This is a very good question. Well, it depends. So will you save money? So it depends on the relative price of gas and electricity. So these are the prices at which gas and electricity has been capped in the latest government fiasco. So let's imagine that we want to provide 10,000 kilowatt hours of heat to a home. Then using gas requires 10,000 kilowatt hours divided by the boiler efficiency. And using electricity with a heat pump would require 10,000 divided by the coefficient of performance. So if the boiler efficiency is 0.9, that would use 11,000 kilowatt hours and cost £1,144. And using electricity with a seasonal coefficient of performance of 3.5 would use only 2,800 kilowatt hours and cost £971. So for a typical installation on average, you will save money, but it's not a massive saving at all. But this question here was, will you save money? The next one is, will I save money? Do I save money? Well, I save loads of money. In fact, I barely have bills these days. Why? Because I have a battery and I have solar panels. And in the winter, I download cheap electricity and store it in the battery. Off-peak electricity, I can get 4 hours of electricity for just 7.5p a unit. And I run the heat pump for most of the time from stored electricity, costing that. So here's in January 2022, this is through the day. This is the average amount of electricity I used. So you can see that in the middle of the night, I used loads of electricity because this is charging up the battery and also doing domestic hot water heating and running washing machines and so on. And then during the day, I don't use any electricity. But then on the very coldest days, the battery runs out and I need to keep the heat pump going by actually buying some electricity at full price. And so that my next year, I expect my average price will be about 10p per kilowatt hour. This winter it was about 6.5p per kilowatt hour. So using electricity my running costs are about £286. And actually solar, even in December, solar will pay for about 10% of that. And this year the government are giving us £400 for some reason. So I basically won't have any bills this year. So how do I know it's working? Well, you'll know it's working. Most people just worry about their house. If it feels okay, they're happy. But some people want to know how it's working every day, in which case I would recommend buying an energy monitor, which will set you back about £1,000 plus installation. And it will give you all this kind of data about how it's operating. But I would say don't try to install it yourself. It will be too painful. And now we come to the point of this. How much CO2 does it save? It saves loads of CO2. So this graph here shows the carbon intensity of UK electricity since 1998. And you see it was up at over 400 grams of carbon dioxide were emitted for every kilowatt hour of electrical usage back then. Now it's about half that, it's 230 last year. 230 grams of carbon dioxide emitted for every unit of electricity. And we expect that by 2030 it should be down at 100. Now, by chance, the figure for gas and electricity is about the same now. So to provide 10,000 kilowatt hours of heat using gas requires 10,000 kilowatt hours divided by the efficiency. It's this many kilowatt hours. And if no gas leaked on delivery to your home, then that would be your estimate for the carbon intensity of the gas, and then you'd emit about 2.5 tons a year. But actually it's becoming apparent now that about 1% of carbon dioxide, 1% of the methane leaks. And so your actual emissions are probably about 4.6 tons, because methane is a very powerful greenhouse gas in itself. Using electricity, you'd have this much lower 0.6 tons a year, but if the gas leaks on the way to the power station, you'd get about 1.2 tons emissions per year. but that is a 75% reduction in CO2 emissions, and that's from the biggest CO2 emitter. So this is a massive change in CO2 emissions. And you can see that if you bring this one back, if you just install now, just running it and the time up to 2030, it'll go down further. It should be a 90% reduction by 2030, and you don't have to do anything to get that. So, okay, here's the summary. Finally, we're at the end. For most people, the biggest step they can take to reducing their carbon dioxide emissions is to switch to using a gas boiler, switch from using a gas boiler to using a heat pump. It's the biggest, best thing you can do. Finally, tips. While you're getting ready for your heat pump, read your gas meter once a week and write down the number. And if you can, plot it in a spreadsheet. So I've been doing this every Saturday morning. I read the gas and electricity meters, and this shows me the gas consumption since 2018. And so I can see that it went up in the winter there. All the different steps I've taken, I can see how my gas use has been eliminated until now. The gas use is absolute zero. I go and read the gas meter and it's the same every week. And the second tip is, if you're worried about your house, buy a thermometer. You loads of different types. When you download this talk, these are links. So you can buy little things, just a little pill that you leave somewhere, and it'll log the temperature every 10 minutes. Leave it in the attic or leave it in the kitchen and just see how the temperature varies. It reads out on your phone. Or buy a thermocouple and just read the temperature, measure the temperature of your radiators, or use an infrared thermometer. They're all great. You'll have good fun. So this might cost 20 quid, this is 20 quid, this is a bit more, about 40 quid. But if you're going to be doing things in your house, having a good thermometer is great help. And these are just some links that will help you. Thank you very much. Sorry it took so long.